All right. Hi, everyone. Thank you so much for joining us today. Today, we have a tech talk on database modeling by Ben Jackson and Eleanor Christopher. Ben and Eleanor, whenever you're ready, take it away.
Thanks, Ashley. Hello, I'm Eleanor Christopher.
And I'm Ben Jackson. And we would like to start by thanking Remake Labs for sponsoring this talk. It's an honor to be here with you all.
We're here today to discuss data modeling. We'll begin with a brief overview of concepts, followed by diving into our specific focus for this talk, the somewhat counterintuitive but very powerful technique of denormalization. More on that later, though. For now, let's discuss the basics of data modeling.
Data models provide a common ground for communications and collaboration. They help to ensure everyone is working toward the same goals and using the data in uniform, consistent ways. Think of it like a game of Tetris. If we build as we go, we can easily leave gaps. These gaps need to ultimately be filled, but by the time we can fill them, they are no longer easily reachable. Filling the holes in our data now requires deconstruction of other work, followed by laborious rebuilding. Now, let's review the two major types of databases.
Short for structured query language, SQL databases are renowned for their ability to handle relational data and ACID compliance. ACID, of course, stands for atomicity. Each transaction is all or nothing. Consistency, data is valid according to all of our defined rules. Isolation, one transaction does not affect another. And durability, committed data cannot be lost, even after a power failure. So SQL is great, but Ben, what about the other major database option?
NoSQL, which formerly meant not SQL, but now means not only SQL. These are excellent choices for their flexibility and ease of setup. Instead of the strict data structure of SQL, NoSQL databases can store primitives, arrays, and even objects. Regardless of our database choice, there is a technique that helps ensure consistency of data.
This brings us to normalization. Simply put, this is the process of ensuring there's no duplication of data across the database. As we have heard in previous talks on normalization in this series, the forms of normalization build upon each other. Starting with the first normal form, it's important that each cell only has one value and each column name is unique. This helps to eliminate duplicate data and simplify queries. The second form requires that each non-key attribute be dependent on the primary key. This means that each column should be directly related to the primary key and not to other columns. The third form requires that all non-key attributes are independent of each other. Every non-key attribute in a table should depend on the key, the whole key, and nothing but the key. From there on, subsequent forms continue to build on this, further ensuring consistency. However, Ben, do you know what's an even cooler technique than normalization?
Denormalization. This is, contrary to first impressions, not the reversing or neglecting of normalization. Instead, it is the process of making specific, developer-chosen redundancies in the data in order to optimize for specific operations. It is done after normalization is completed and is best done judiciously. What are some common situations where we might denormalize, though?
Let's look at some problems and helpful techniques. So here's a problem. We have two tables, customer and order. The order table contains all the data about a single order, but it references the customer table for all information about the customer who placed the order. When we interact with the order information, the only relevant information about the customer is their name. A common operation is to simply join the two tables with the customer ID to get the customer's name and ignore the rest of the customer table. Done once, this is no problem. Done thousands of times per minute for each and every order, on the other hand, can be very expensive. So should we just eat the productivity and time loss from the constant joins?
We say no. Instead, we can simply pre-join the two tables in a way that is commonly referenced. In this case, we can add the customer name column to the order table. This allows us to skip the computation for a very common join with only a minimal increase in storage and complexity. In this simple example, we can see that we save time, but we increase space as now we are storing the customer name in our database twice. Just remember, time is expensive, space is cheap, and redundancy is not necessarily evil.
How about another problem? Similar to the first, we have two tables. This time, there are students and assignment grades. Again, we have a common join goal. We want to get the total marks for each student. Unlike the first problem, there's a compounding factor here. We have to do math, and math with joins can be even more expensive than simple joins. Whatever shall we do?
As Henry II probably said, will no one rid me of this turbulent math? And the answer is sort of. Instead of having to join and do math every time, we can simply pre-calculate the total marks and store them inside the student's table. By pre-calculating derivable data, we can save even more time than by eliminating common joins. The downside to this approach is that each time a new assignment is added to the assignment grades table, the students table needs to be updated as well. Just remember, time is expensive, space is cheap, and redundancy is not necessarily evil.
Another thing to consider is scalability.
Data is big. You just won't believe how vastly, hugely, mind-bogglingly big it is. I mean, you may think it's a long way down the road to the chemists, but that's just peanuts to data. When dealing with data sets this large, a common approach is to shard or split the data.
Sharding is a common technique for dealing with very large data sets, but it comes with a performance cost for joins across the network. If we think joins on a monolithic database could be slow, imagine doing it between physical machines. At truly enterprise scale, these machines might not be in the same city, state, or even country. Fortunately, well-placed and modeled denormalization allows us to once again skip the entire process for common joins.
Just remember, time is expensive, space is cheap, and redundancy is not necessarily evil. Why does this sound familiar?
So let's talk about some of the reasons to denormalize. From an end user perspective, the obvious answer is the performance benefits for common operations. By reducing or eliminating common joins, the amount of time needed to retrieve data is greatly reduced. This helps to avoid the dreaded 3-second mark for loads. On the developer end, there's the potential benefit of reducing the number of tables. This can contribute to less dev time spent on maintenance and enhanced scalability. But denormalization can't be all benefits, right, Ben?
Unfortunately not. We've been saying to be judicious in your use of denormalization, and there are some good reasons why. Remember how we said denormalization can potentially reduce complexity? Well, it can easily introduce additional complexity too. By introducing redundant data, we have to work extra hard to ensure that the data is updated consistently across the database. If we fail, the end user will find it. Also, there's a reason space being cheap came up earlier. We're going to need more of it. So increased dev complexity and additional space have one thing in common: higher costs. While higher costs will eventually be passed on to the end user, they can be much harder to detect compared to significant performance issues.
To review, data normalization can be a powerful tool. It can boost user retention through faster data retrieval, save developer headaches from complex queries, and potentially reduce the number of tables needed to be maintained. While, just like everything in tech, there are trade-offs such as cost and developer time, it's important to still strongly consider limited, intentional denormalization in modeling your next database.
These are our works cited. Feel free to reach out to us here. And we would like to thank Remake Labs once again for giving us this wonderful opportunity.
Thank you so much, Ben and Eleanor. That was an amazing tech talk on database modeling. And so unfortunately, that's all the time we have for today. So thank you so much for everyone to come out tonight.
Thank you.